Section 10.3 Electronegativity and Polarity. We can learn more about the chemistry of compounds by looking at how electrons are shared between atoms. The bonding electrons are shared equally in a bond between identical non-metal atoms. However, when a bond is between atoms of different elements, the electron pairs are usually shared unequally. Then the shared pairs of electrons are attracted to one atom in the bond more than the other. Electronegativity. The electronegativity of an atom is its ability to attract the shared electrons in a chemical bond. Nonmetals have higher electronegativities than do metals because metals have a greater attraction for electrons than metals. On the electronegativity scale, fluorine was assigned a value of 4, and the electronegativities for all other elements were determined relative to the attraction of fluorine for shared electrons. The nonmetal fluorine, which has the highest electronegativity, is located in the upper right corner of the periodic table. The metal cesium, which has the lowest electronegativity of 0.7, is located at the lower left corner of the periodic table. The electronegativity values of the representative elements are shown in Figure 10.1. Electronegativity decreases down the row and decreases as it goes from right to left. So it increases as it goes towards the top of the periodic table and to the right. Going across each period from left to right, there is an increase in the positive charge in the nuclei, and that causes greater attraction for the electrons. This results in an increase in the electronegativity values going across the period from left to right. Within each group, the attraction for electrons decreases going down the group as the size of the atoms increases. Thus, the highest electronegativities are at the top and decrease going down within a group. The electronegativities for the transition elements are low, but we will not include them in our discussion. There are no electronegativities assigned to the noble gases because they typically do not form bonds. Types of bonds. The difference in electronegativity values for two atoms can be used to predict the type of a chemical bond, ionic or covalent, that forms. For a hydrogen-hydrogen bond, the electronegativity difference is 0. 2.1 minus 2.1 is 0, which means that the bonding electrons are shared equally. Thus, we see a symmetrical electron cloud around the hydrogen atoms. A covalent bond between atoms within identical or very similar electronegativity values is a nonpolar covalent bond. However, in a covalent bond between atoms of different electronegativity values, the electrons are shared unequally, and the bond is a polar covalent bond. The electron cloud for a polar covalent bond is unsymmetrical. For the hydrogen-chlorine bond, there is an electronegativity difference of 9. Which means that the hydrogen-chlorine bond is a polar covalent. When finding the electronegativity difference, the smaller electronegativity is always subtracted from the larger. Thus, the difference is always a positive number. In a nonpolar covalent bond of H2, electrons are shared equally. In the polar covalent bond of HCl, electrons are shared unequally. Dipoles and bond polarity. The polarity of a bond depends on the difference in the electronegativity values of its atoms. In a polar covalent bond, the shared electrons are attracted to the more electronegative atom, which makes it partially negative, due to the negatively charged electrons around the atom. At the other end of the bond, the atom with the lower electronegativity becomes partially positive due to a lack of electrons around that atom. The bond becomes more polar as the electronegativity difference increases. A polar covalent bond has a separation of charges is called a dipole. A positive and a negative ends are indicated by the lowercase Greek letter delta with the positive or negative sign, delta positive or delta negative. Sometimes we use an arrow that points from the positive charge to the negative charge, indicating a dipole. Variations in bonding. The variations in bonding are continuous. There is no definite point at which one type of bond stops and one starts. When the electronegativity difference is from point 0 to point 4, the electrons are considered to be shared equally in a nonpolar covalent bond. For example, an HH bond with an electronegativity difference of 0 is 0, and the carbon-hydrogen bond with an electronegativity difference of 0.4 are classified as nonpolar covalent bonds. As the electronegativity difference increases, the shared electrons are attracted more closely to the more electronegative atom, which increases the polarity of the bond. When the electronegativity difference from 0.5 to 1.8, the bond is classified as polar covalent bond. For example, oxygen-hydrogen bond with an electronegativity difference of 1.4 is a polar covalent bond. When the difference of electronegativity is greater than 1.8, electrons are transferred from one atom to the other, which results in an ionic bond. For example, the electronegativity difference for the ionic compound sodium chloride is 2.1. 3 minus 0.9 is 2.1. Thus, for large differences in electronegativity, we would predict an ionic bond. Table 10.5 gives an example of predicting bond types from the electronegativity difference. Covalent nonpolar, electrons shared equally. Covalent polar, electrons are shared unequally. Ionic, electrons are transferred. In a hydrogen dipole of HH bond, they're shared equally because the electronegativity difference is 0. For a bromine chloride bond, bromine chloride bond, the difference is 0.2 of electronegativity, which they're shared almost equally, and is considered a nonpolar covalent bond. For a hydrogen bromide bond, which is shared unequally because there's an electronegativity difference of 0.7, it's considered a polar covalent bond, which is greater than 0.4 but less than 1.8. For a hydrogen chloride bond, shared unequally because its electronegativity difference is 0.9, it's a polar covalent bond because it's greater than 0.4 but less than 1.8. For a sodium chloride bond, where you actually have electron transfer, you have an electronegativity difference of 2.1, and since that's greater than 1.8, that is an ionic bond. Likewise, magnesium oxide is an electronegativity difference of 2.3. It's greater than 1.8, so it's considered ionic. Polarity of molecules. We see that covalent bonds in molecules can be polar or nonpolar. Now we will look at how the bonds in a molecule and its shape determine whether the molecule is classified as polar or nonpolar. Nonpolar molecules. In a nonpolar molecules, all the bonds are nonpolar, or the polar bonds cancel each other out. Molecules such as hydrogen, chlorine, and methane are nonpolar because they contain only nonpolar covalent bonds. A nonpolar molecule also occurs when polar bonds, or dipoles, cancel each other out because they are in symmetrical arrangement. For example, carbon dioxide, a linear molecule, contains two equal polar covalent bonds whose dipoles point in opposite directions. As a result, the dipoles cancel out, which makes the carbon dioxide molecule nonpolar. Another example of a nonpolar molecule is the carbon tetrachloride molecule, which has four polar bonds symmetrically arranged around the central atom. Each carbon chloride bond has the same polarity, but because they have a tetrahedral arrangement, their opposing dipoles cancel out. As a result, the molecule of carbon tetrachloride is nonpolar. Polar molecules. In a polar molecule, one end of the molecule is more negatively charged than the other end. Polarity in a molecule occurs when dipoles from individual polar bonds do not cancel each other out. For example, hydrogen chloride is a polar molecule because it has one covalent bond that's polar. In molecules with two or more electron groups, the shape, such as bent or triagonal pyramidal, determines whether or not the dipoles cancel. For example, we have seen that water has a bent shape. Thus, water molecule is polar because the individual dipoles do not cancel. The ammonia molecule has a tetrahedral electron geometry with 3 bonded atoms, which gives a diagonal pyramidal shape. Thus, an ammonia molecule is polar because the individual nitrogen-hydrogen dipoles do not cancel. In the molecule of CH3F, the CF bond and the polar covalent, but the 3 carbon-hydrogen bonds are nonpolar covalent. Because there is only one dipole which does not cancel, CH3F is a polar molecule.